Hello, and welcome to Late Night Physics. Before we dive into tonight's journey through the very fabric of the universe, take a moment to like this video and subscribe if you love exploring the quiet wonders of physics. And I have to ask, where are you watching or listening from tonight? Whether it's from a cozy bedroom, a late-night study desk, or even somewhere far away under a different sky, the electron you'll hear about tonight is the same everywhere in the universe, a tiny spark connecting you to the cosmos. Tonight, we're asking a deceptively simple yet profoundly mysterious question. Why does the electron have the charge it does? It's a question that reaches from the lab benches of early 20th century physicists to the deepest reaches of modern theoretical physics, from experiments that measured this charge with astonishing precision to ideas that stretch across extra dimensions and speculative universes. We'll explore how something so minuscule holds the key to so much of the world around us. So settle in, relax, and let your mind drift through the quiet elegance of particles, forces, and cosmic mysteries as we begin our journey into the strange, precise, and utterly fascinating world of the electron's charge. Imagine a property so fundamental that it threads through everything around us, quietly guiding the behavior of the world at every scale. This property is electric charge, an invisible feature of matter that determines how particles interact, how atoms bind, and how the lights in our homes illuminate. It is a principle as old as the discovery of static electricity, yet as current as the latest quantum experiments in laboratories around the world. Electric charge is not something we see directly, but we feel its effects constantly. It is the reason a balloon sticks to a wall after you rub it on your sweater, the reason lightning dances across the sky during a summer storm, and the reason your smartphone functions with precise reliability. Electric charge comes in two types, which we call positive and negative. These labels are a historical convention, set in place long before the underlying nature of electrons and protons was fully understood. Opposite charges attract, pulling together as if drawn by an invisible thread, while like charges repel, pushing away from one another with a force that can be measured and quantified. This behavior is captured elegantly in Coulomb's law, which tells us that the force between two charged particles is proportional to the product of their charges and inversely proportional to the square of the distance separating them. The law is simple in expression, yet it governs phenomena ranging from the tiny scales of individual electrons to the grand scales of stars and nebulae. A fundamental aspect of electric charge is that it is conserved. The total amount of charge in a closed system never changes. When one particle loses a little of its charge, another gains exactly that same amount, ensuring balance throughout the universe. This principle of conservation is not merely an abstract idea. It is observed in countless experiments, from early laboratory work to the high-precision measurements conducted by the National Institute of Standards and Technology in the United States. Every electron that ever existed carries the same negative charge, a remarkable consistency that speaks to a deep order in the natural world. Yet, as straightforward as the concept of charge might seem, it immediately raises a profound question. Why does the electron carry exactly this charge? Why is the negative charge of the electron equal in magnitude to the positive charge of the proton? And why does it have the precise value that it does, a value so consistent that it underpins the stability of atoms, molecules, and the very chemistry that makes life possible? This is not just a curiosity for scientists in white coats. It is a question that touches the very structure of matter, and by extension, our own existence. Every atom, every molecule, every spark of electricity relies on this balance, a balance so precise that even the slightest deviation would create a radically different universe. The relevance of charge extends from the microscopic to the cosmic. In chemistry, it governs how electrons orbit nuclei, how chemical bonds form, and how molecules interact with one another. The arrangement of electrons, each carrying its negative charge, determines the behavior of every substance, whether it is water forming gentle waves in a pond or proteins folding with exquisite specificity inside our cells. In electronics, charge is the currency that powers circuits, enables digital computation, and allows the manipulation of information at incredible speeds. In astronomy and cosmology, charged particles shape the structure of plasmas in stars, influence the dynamics of cosmic magnetic fields, and dictate the behavior of ionized gases in interstellar space. The electron's charge is a subtle yet profound thread connecting these realms, linking the tiniest quantum interactions to the movements of galaxies. To appreciate the electron's charge, we can look at historical experiments that brought this invisible property into measurable reality. In the late 19th century, physicists such as Charles-Augustin de Coulomb and Michael Faraday explored the behavior of charged objects, laying the foundation for understanding electrical forces and currents. Coulomb devised torsion balance experiments that allowed him to quantify the force between charges with unprecedented precision, while Faraday's work on electrolysis revealed that charges are transferred in discrete countable amounts. These early investigations hinted at a granularity in charge that would later be confirmed by experiments with individual particles. The discovery of the electron itself in the year 1897 by J. Thomson was a milestone in understanding charge at a fundamental level. Thomson's experiments with cathode rays revealed that atoms were not indivisible, but contained tiny, negatively charged constituents. He measured the ratio of charge to mass for these particles, establishing a numerical foundation that later experiments would refine. This discovery prompted new questions about the nature of the electron's charge, its universality, and its role in the architecture of matter. From these early findings, scientists began to appreciate that charge is not just a convenient label or a mathematical abstraction. It is a measurable, universal property. Robert Millikan's oil drop experiment, conducted in the year 1908 and refined in subsequent years, demonstrated with remarkable precision that the electron's charge comes in fixed, identical units. Millikan's meticulous work revealed that the charge of a single electron is approximately 1.602 times 10 to the negative 19th coulombs, a value so precise that it has become one of the cornerstones of modern physics. This constancy is astonishing, considering the vast number of electrons in existence and the dynamic environments in which they reside. Even as we describe these historical discoveries, it is worth appreciating the elegance and simplicity of the underlying ideas. Positive and negative charges, attraction and repulsion, conservation and quantization, all these principles emerge naturally and guide the behavior of matter from the smallest particles to the largest cosmic structures. The electron's charge is both familiar and mysterious, tangible in its effects yet enigmatic in its origin. It sets the stage for deeper explorations into quantum mechanics, field theory, and the speculative frontiers of physics where scientists today, in laboratories like CERN in Switzerland and research groups across the globe, continue to investigate why the electron carries the charge it does. By the end of this exploration, the listener comes to see charge not merely as a static property, but as a dynamic principle woven into the universe itself. It is the invisible hand that shapes atoms, fuels electricity, and orchestrates interactions across cosmic scales. And while its value is a fixed, measurable reality, the question of why it is exactly this value remains an open invitation to curiosity, inquiry, and wonder. In this sense, the electron's charge is both a key and a mystery, a gateway to understanding the structure of reality, and a reminder that even the smallest particle carries profound significance in the vast tapestry of the universe. At the turn of the 20th century, the idea that atoms might not be indivisible began to gain traction, and a series of experiments in England revealed a world far smaller and stranger than anyone had imagined. In the year 1897, the English physicist J. Thomson conducted his now famous cathode ray experiments at the Cavendish Laboratory in Cambridge. Using evacuated glass tubes and carefully controlled electrical fields, he observed that rays of light emitted from the cathode, the negative electrode, were deflected by magnetic and electric forces. This deflection revealed that the rays were composed of tiny, negatively charged particles, much smaller than atoms themselves. Thomson's measurements allowed him to calculate the ratio of electric charge to mass for these particles, and the results indicated a value far greater than that of any known ion, suggesting a particle of astonishingly small mass and definite negative charge. While Thomson is often celebrated as the discoverer of the electron, the path to this insight was paved by lesser-known contributors. Eugen Goldstein, working in Germany in the year 1886, observed what he called canal rays, streams of positively charged particles moving in the opposite direction to cathode rays. Though these observations did not immediately reveal the electron, they hinted at a deeper structure within atoms and helped establish that both positive and negative charges existed as discrete components. In the United States, Harvey Fletcher, a student and collaborator of Robert Millikan, later refined measurements of electron properties, showing how meticulous experimentation could bring clarity to the subatomic world. Each of these scientists, in their own laboratories and with their own instruments, chipped away at the veil obscuring the inner life of the atom. The discovery of a particle smaller than the atom was met with excitement and a touch of disbelief. For centuries, the atom had been considered the ultimate indivisible unit of matter, a notion first proposed by early philosophers like Democritus and later supported by chemical theory. To find that these atoms contained even smaller components, each carrying an intrinsic electric charge, was both thrilling and unsettling. It meant that matter was more intricate than previously imagined, and it demanded a new framework for understanding forces, stability, and interactions. Suddenly, the world of atoms was no longer a collection of solid, featureless spheres, but a dynamic arena where charged particles danced, attracted and repelled one another, and gave rise to all chemical and physical behavior. The implications of these discoveries extended far beyond the laboratory. Thomson's cathode rays demonstrated not only that electrons existed, but also that their charge could be measured and quantified. By observing the curvature of the rays in electric and magnetic fields, he established that the charge-to-mass ratio of these particles was constant, a foundational insight for the emerging concept of charge quantization. This principle, that charge comes in discrete indivisible units, would later be confirmed by Millikan and others. But Thomson's work provided the first clear evidence that such a concept was necessary to describe the behavior of matter at a fundamental level. It became apparent that electric charge was not just a convenient abstraction, but a measurable universal property that governed the interactions of all matter. One of the subtle marvels of these experiments lies in their simplicity and elegance. Thomson used relatively straightforward apparatus, a glass tube, electrodes, and magnetic coils. Yet he revealed the existence of a particle that would become central to the structure of matter. The careful calibration of fields, the precise observation of beam deflection, and the methodical calculation of charge-to-mass ratios demonstrated the power of experimental physics to illuminate realities far beyond human perception. Each tiny deflection of a cathode ray on a fluorescent screen was a whisper from the quantum world, hinting at an underlying order and a hidden precision that governs every atom. As scientists pieced together the properties of the electron, a question naturally arose. Why does the electron carry exactly the charge it does? Thomson's measurements, though indirect, established that the negative charge was consistent across all electrons, and subsequent work would show the equality and magnitude of the positive charge carried by protons. This balance is essential for the stability of atoms, the formation of molecules, and the very existence of matter as we know it. It is remarkable to consider that the experiments of a few observant physicists, using tools invented over a century ago, could reveal a property that is universal throughout the cosmos, from the smallest laboratory apparatus to the heart of distant stars. In reflecting on these early experiments, it is also worth noting the human element in the pursuit of knowledge. The laboratories of Cambridge, Berlin, and later the United States were places of curiosity, careful measurement, and creative problem-solving. Scientists like Thomson, Goldstein, and Fletcher were guided not only by equations and apparatus, but by a sense of wonder about the invisible structures of reality. Their work demonstrates that uncovering the electron, and by extension understanding its charge, requires patience, imagination, and a willingness to look beyond the immediately visible. By the end of these explorations, the stage was set for a deeper investigation into the nature of charge itself. The electron had been revealed, its negative charge measured and confirmed, and the tantalizing hint of quantization emerged as a guiding principle. These discoveries laid the foundation for the next great leaps in physics, the oil drop experiments, the development of quantum mechanics, and the eventual construction of the Standard Model. They remind us that even the tiniest particles can hold profound significance, and that the journey to understand why the electron has the charge, it does begins with the curiosity and ingenuity of those early explorers in physics. In the year 1908, a quiet revolution was taking place in a laboratory at the University of Chicago. The American physicist Robert Millikan, along with his diligent collaborator Harvey Fletcher, undertook an experiment that would reveal the discrete nature of electric charge with a precision that astonished the scientific community. This was the famous oil drop experiment, a deceptively simple setup that allowed the measurement of the charge carried by a single electron. Tiny droplets of oil were sprayed into a chamber where they fell under the influence of gravity. By observing the motion of these droplets in the presence of carefully controlled electric fields, Millikan and Fletcher could determine how much electrical force was required to counteract gravity and suspend the droplets in mid-air. Each careful observation brought them closer to a remarkable conclusion. The charge on each droplet was always an integer, multiple of a fundamental value, a tiny, indivisible unit that we now call the elementary charge. The elegance of this experiment lies not only in its conceptual simplicity, but also in the precision with which Millikan approached measurement. He meticulously accounted for factors such as air viscosity, droplet size, and Brownian motion, the random jostling caused by molecules colliding with the suspended oil. It was a painstaking process, requiring hundreds of observations and careful calculation, yet the results were unequivocal. Each droplet's charge could be expressed as an exact multiple of a basic quantity, roughly 1.602 times 10 to the negative 19th coulombs, and no smaller fraction was observed. This value, tiny beyond ordinary comprehension, underpins all electrical interactions in the universe, from the conduction of currents in a copper wire to the intricate folding of proteins in our cells. Harvey Fletcher, often overshadowed by Millikan's fame, played a crucial role in refining the experimental technique and ensuring the reliability of the results. Fletcher's careful measurements and insistence on rigorous methodology contributed to the high level of confidence in the findings. Together they demonstrated that electric charge was not a continuous variable that could take any value, as had been assumed in some early theories, but a fundamentally quantized property. This was a profound insight, one that laid the groundwork for the emerging field of quantum mechanics and altered our understanding of matter at its most basic level. The implications of quantized charge were revolutionary. It meant that all electrons, wherever they might exist in the universe, carry the same negative charge. Protons similarly carry an equal and opposite positive charge, ensuring the stability and neutrality of atoms. The recognition of these discrete units of charge challenged classical physics, which had treated electric phenomena as smooth and continuous, and opened the door to a new era of theoretical exploration. The idea that nature operates with such exactness and consistency, that the universe adheres to integer multiples of a fundamental charge, hinted at a deeper order and structure underlying the apparent chaos of the world. Millikan's oil drop experiment also provided an anchor for other measurements and theories. The value of the elementary charge allowed physicists to calculate the mass of the electron when combined with J.J. Thomson's earlier charge-to-mass ratio, providing a clearer picture of the particle's properties. It also established a reliable foundation for understanding chemical reactions, electrical currents, and the behavior of ions in solution. In every field where electricity played a role, from the nascent technology of light bulbs to the complex calculations of atomic spectra, the elementary charge became a constant, a fixed point in a universe otherwise filled with variables. Beyond its scientific impact, the experiment offers a lesson in patience, precision, and curiosity. Observing minute oil droplets through a microscope for hours on end, calculating forces that are incomprehensibly small by human standards, Millikan and Fletcher revealed the hidden quantization of nature through meticulous care and persistent observation. The experiment demonstrates that even the most abstract principles can be made tangible, and that understanding the universe often requires both clever conceptual design and painstaking attention to detail. It is also an invitation to reflect on the philosophical depth of the finding. If charge comes in discrete units, why is this particular unit, this particular number, the one chosen by nature? The oil drop experiment tells us that charge is quantized and universal, but it does not explain why the electron's charge has exactly the magnitude it does. This question continues to fascinate physicists today, driving inquiries in quantum electrodynamics, the search for fundamental constants, and explorations into theories that stretch from grand unification to extra dimensions. The electron's charge, measured with such painstaking care by Millikan and Fletcher, is both a concrete value and a doorway into profound mysteries. As the results of the oil drop experiment became widely known, the scientific community embraced the concept of the elementary charge as a cornerstone of physics. It was a triumph of experimental ingenuity, of careful observation and thoughtful interpretation, and it revealed a universe that is simultaneously orderly, elegant, and filled with subtle wonders. By demonstrating that charge is quantized, Millikan and Fletcher showed us that the fabric of reality is made of discrete threads, woven with precision into the tapestry of atoms, molecules, and the forces that shape our world. And it is from these threads that the journey continues, as physicists ponder not only how charge behaves, but why it has the value it does, a question that remains as intriguing now as it was over a century ago. For much of the 19th century, electricity and magnetism were understood through the elegant framework of classical physics, a domain beautifully captured by James Clerk Maxwell. Maxwell's equations, formulated in the year 1865, described electric and magnetic fields as continuous entities that could vary smoothly across space and time. These equations unified previously separate phenomena into a single, coherent theory, explaining how currents generate magnetic fields, how changing magnetic fields induce electric currents, and how light itself is an electromagnetic wave travelling through space. Classical electromagnetism provided a predictive and remarkably successful model for the macroscopic world, guiding engineers and scientists in designing telegraph systems, electric motors, and early electrical circuits. Yet, despite its power, classical theory faced limitations when applied to the microscopic realm of atoms and subatomic particles. While Maxwell's equations could describe how electric and magnetic forces act, they offered no explanation for why charge itself appears in discrete amounts, or why the electron carries exactly the value measured by Millikan. In classical theory, charge could be imagined as a continuous quantity, divisible indefinitely, much like a fluid spreading across space. There was no reason in the classical picture why charges could not take on arbitrary fractions, or why the electron's negative charge should precisely balance the proton's positive charge. Observations in laboratories, however, told a different story. Electrons appeared with identical charges, and chemical reactions behaved as if this charge came in indivisible units. Something beyond the smooth continuum of classical fields was at work, hinting at deeper principles that classical physics could not capture. The emergence of quantum theory provided the framework necessary to understand these discrete properties. In the year 19020, Wolfgang Pauli introduced the exclusion principle, which stated that no two electrons could occupy the same quantum state simultaneously. This insight was more than a rule about electron arrangement. It highlighted a fundamental granularity in the microscopic world. Electrons, and by extension their charges, behave as discrete entities with specific well-defined properties. Quantum mechanics, through its probabilistic yet mathematically precise structure, allows us to calculate the behavior of electrons in atoms, predict energy levels, and explain the stability of matter in a way that classical physics could never achieve. Charge quantization, therefore, is not an arbitrary observation, but a natural consequence of the quantum framework, a reflection of the deeper rules governing the subatomic world. The quantum perspective also introduces the concept of wave-particle duality, revealing that electrons can exhibit both particle-like and wave-like behavior, depending on the context of measurement. Experiments such as the double-slit interference experiment, first performed with electrons in the mid-20th century, demonstrate that these particles are governed by probabilities and wave functions, not the continuous trajectories imagined by classical physics. This dual nature of matter ensures that electrons cannot carry arbitrary amounts of charge. Their properties are quantized, and each electron consistently exhibits the same negative charge. The very notion of indivisible units of charge, first glimpsed through Millikan's oil drop experiment, finds a natural explanation in this framework, providing both a conceptual and mathematical foundation for the universality of the electron's charge. In addition to charge quantization, quantum theory explains other phenomena that classical physics could not, such as the discrete energy levels of atoms discovered by Niels Bohr in the year 19013. Electrons occupy specific orbits or shells around atomic nuclei, absorbing or emitting energy only in defined quanta when they transition between these levels. The stability of atoms and the predictability of chemical behavior both depend on these quantized properties. Charge, in this sense, is intertwined with energy and angular momentum in a structured, discrete framework. It is not a free-floating parameter, but a fixed property of the electron that manifests consistently in every atom, molecule, and chemical reaction. This realization also laid the groundwork for modern particle physics, where the Standard Model describes a zoo of fundamental particles, each with defined properties including mass, spin, and electric charge. The electron, a fundamental lepton, carries a negative charge of exactly one elementary unit, while quarks display fractional charges in specific combinations that result in whole charges for protons and neutrons. The quantum view, informed by the work of physicists such as Pauli, Bohr, and later Richard Feynman, provides a framework in which these patterns are not accidental, but emerge from underlying symmetries and conservation laws, charges conserved in all interactions, appearing in integer multiples of the elementary charge and obeying the rules imposed by the mathematical structures of quantum field theory. Yet, even with quantum mechanics providing clarity about why charge is quantized, the deeper question remains tantalizingly open. Why does the electron carry the particular value it does, 1.602 times 10 to the negative 19th coulombs? The theory tells us that this charge must be the same for every electron, but it does not predict its precise numerical magnitude. This subtle distinction emphasizes the layered nature of our understanding. Classical physics could describe forces and fields. Quantum mechanics explains quantization and particle behavior. But the exact value of the electron's charge hints at a further underlying order, one that continues to inspire exploration in quantum electrodynamics, symmetry theories, and high-energy physics experiments around the globe. In reflecting on these contrasts between classical and quantum views, one appreciates both the simplicity and the depth of the universe's design. Classical theory provides the broad strokes, an intuitive framework for how charges interact at human scales. Quantum theory adds texture, revealing that beneath the smooth fields of Maxwell, there lies a world of discrete particles, quantized energies, and invariant charges. Together, these perspectives illuminate why the electron's charge is consistent, universal, and essential to the structure of matter. The journey from classical to quantum understanding is a reminder that nature often resists simple explanation, rewarding careful observation and theoretical creativity with glimpses into its underlying elegance. In the quiet halls of theoretical physics, a framework emerged that would elegantly unify much of our understanding of the subatomic world. This framework is known as the Standard Model of Particle Physics, a theory developed throughout the mid-20th century that classifies all known fundamental particles and describes how they interact through three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. At the heart of this model sits the electron, a fundamental lepton, carrying a negative electric charge that is the same for every electron in the universe. Leptons, including electrons, muons, tau particles, and their corresponding neutrinos, are particles that do not experience the strong nuclear force, yet their charges and interactions with other particles are critical to the structure of matter and the stability of atoms. The development of the Standard Model relied on a series of theoretical insights and experimental confirmations. Sheldon Glashow and Abdus Salam, building on the work of Steven Weinberg in the 1960s, formulated a model that unified electromagnetic and weak interactions into what is now called the electroweak theory. Their contributions clarified the rules by which charged leptons interact with the W and Z bosons, the carriers of the weak nuclear force, and elegantly explained why particles like electrons have precisely assigned charges. The successful prediction of the neutral weak boson, later confirmed experimentally, reinforced the power of symmetry principles in constraining particle interactions, showing that charges are not arbitrary, but arise from underlying gauge symmetries. While electrons carry a simple negative charge, the Standard Model also describes particles with more exotic fractional charges. Quarks, which combine to form protons and neutrons, carry charges of plus 2/3 or minus 1/3 of the electron's charge. These fractional charges might seem puzzling at first, yet they are essential for the formation of stable matter. The combination of three quarks in protons and neutrons produces whole number charges, balancing positive and negative values to ensure the electrical neutrality of atoms in ordinary matter. The assignment of quark charges is not arbitrary, but arises naturally from the model's mathematical structure, specifically through the concept of hypercharge, which combines with weak isospin to produce the observed electric charge of particles. Hypercharge, a quantum number introduced within the electroweak theory, reflects the underlying symmetries of the Standard Model. It determines how particles couple to gauge bosons and is intimately linked to the conservation of electric charge. For leptons like the electron, the hypercharge, combined with weak isospin, reproduces the familiar negative charge. This framework explains why electrons, muons, and tau particles share identical charges, and why quarks exhibit the precise fractional charges necessary to form the building blocks of matter. It demonstrates the power of symmetry in physics. Charges are constrained by the rules of the theory, yet the model itself does not provide a deeper reason for the exact numerical value of the elementary charge. Despite the explanatory power of the standard model, the electron's charge remains a parameter rather than a predicted quantity. The model constrains relationships between charges, ensuring consistency and stability in particle interactions, yet it does not tell us why the negative charge of the electron is exactly 1.602 times 10 to the negative 19th coulombs. This subtle distinction highlights the frontier between understanding and mystery. We can describe how charges behave, how they interact, and how they combine to form matter, but the origin of the specific value is left to more speculative and high-level theories. It is as if the standard model provides the rules for the game but does not reveal why the pieces are shaped the way they are. Experimental confirmation of the standard model's predictions has been meticulous and precise. High-energy particle accelerators such as the Large Hadron Collider at CERN in Switzerland have produced countless electron-positron collisions, confirming the predicted interactions and decay patterns of leptons. Measurements of scattering cross-sections, decay rates, and magnetic moments consistently reflect the charges assigned within the standard model, reinforcing the universality and reliability of the electron's negative charge. These experiments show that the charge is not merely a convenient construct, but a deeply embedded property, consistent across every observation and interaction. It's also worth noting the subtle interplay between theoretical predictions and experimental verification in developing this model. The work of theorists such as Glashow and Salam required precise high-energy experiments to validate their ideas. Without confirmation from laboratories around the world, including institutions like Fermilab in the United States and DESY in Germany, the model would have remained speculative. This dialogue between theory and experiment exemplifies the scientific method at its most rigorous. Hypotheses guided by symmetry, mathematics, and principles of gauge invariance are tested against nature, and the consistency of results strengthens our confidence in the assigned charges of fundamental particles. The framework of the standard model provides a clear picture of the hierarchy of particles and their charges, yet it also prepares us for deeper questions. Why is the electron's charge exactly what it is? Could it be derived from an even more fundamental principle, perhaps within a grand unified theory, or a theory of extra dimensions? The model shows us the patterns, the constraints, and the rules, but it hints at a richer structure beneath, a deeper layer of reality that might explain not just how charges relate, but why the basic units themselves have the values we observe. In reflecting on these insights, we see that the electron's charge is both simple and profound. It is a single negative unit that combines with quarks and other leptons to form the intricate architecture of matter, yet it is a key to mysteries that extend far beyond everyday experience. The standard model teaches us that symmetry and gauge invariance govern particle behavior, that fractional charges are required for consistency, and that charge conservation is absolute. At the same time, it reminds us that even within a powerful predictive theory, some questions remain open, inviting exploration into the very origins of the universe's fundamental constants, and the hidden rules that dictate the value of the electron's charge. In the early 20th century, the mathematician and physicist Emmy Noether revolutionized our understanding of the connection between symmetry and the fundamental laws of nature. In the year 19018, Noether formulated what is now known as Noether's theorem, showing that every continuous symmetry in a physical system corresponds to a conserved quantity. For example, the symmetry of space, its invariance under shifts in position, leads to the conservation of momentum, while symmetry under rotations produces conservation of angular momentum. In the context of electromagnetism and particle physics, Noether's insight provides the foundation for understanding why electric charge is conserved. The uniformity and invariance of certain properties in space and time impose strict rules, ensuring that the total charge in a closed system remains constant no matter how particles interact or transform. This deep connection between symmetry and conservation extends naturally into the framework of gauge theories. In the 1950s, Chen Yang and Robert Mills developed a generalization of the concept of symmetry, now known as Yang-Mills gauge theory. They introduced the idea that certain types of symmetries, called non-abelian symmetries, require the existence of force-carrying particles to maintain local invariance. These gauge bosons mediate interactions between fundamental particles, and the charges of those particles determine how strongly they couple to the forces. For instance, in the Standard Model, the photon couples to particles with electric charge, the W and Z bosons mediate weak interactions, and gluons interact with quarks according to color charge. The mathematical structure of Yang-Mills theory elegantly constrains the allowed charges, ensuring consistency across particle interactions and stabilizing the fundamental properties of electrons, quarks, and other particles. Beyond the simple assignments of charge, symmetries also give rise to more subtle concepts such as topological charges and anomalies in quantum field theory. Topological charges are conserved not because of simple invariance under continuous transformations, but due to the underlying global properties of the fields themselves. These charges are linked to the shape and connectivity of the field configurations, often taking integer values that cannot change continuously. Anomalies, on the other hand, are situations in which classical symmetries appear to be broken in the quantum theory, potentially threatening the consistency of the model. Physicists such as Gerard 't Hooft and Edward Witten have shown that the cancellation of certain anomalies is necessary for the Standard Model to function properly, and these requirements indirectly constrain the possible electric charges of particles. In this way, symmetry principles are not abstract exercises in mathematics. They actively shape the structure of matter and the interactions that govern it. The application of these principles to the electron is particularly illuminating. The electron's negative charge is not an arbitrary assignment. It arises from the combination of underlying symmetries, conservation laws, and the need for anomaly cancellation in the electroweak sector of the Standard Model. Its charge is precisely defined, and all electrons share this exact value. This universality is a direct reflection of the deep mathematical symmetries embedded in the laws of nature. Experiments consistently confirm that the electron's charge is invariant, whether measured in laboratories on Earth, in cosmic rays arriving from distant galaxies, or in the conditions near the surface of the Sun. The consistency reinforces the notion that symmetries are not merely elegant abstractions but powerful principles dictating the properties of fundamental particles. Gauge principles also illuminate why fractional charges appear in other particles. Quarks, for instance, carry charges of plus 2/3 or minus 1/3 of the electron's charge, values that might seem curious until one recognizes that they satisfy the requirements of anomaly cancellation within the Standard Model. The combination of quarks into protons and neutrons produces whole number charges, ensuring that ordinary matter remains electrically neutral and stable. These fractional charges are a natural consequence of the symmetries and constraints imposed by Yang-Mills theory, demonstrating once again that the mathematical structure of gauge invariance governs the very architecture of matter. It is remarkable to consider that something as simple as the negative charge of the electron can be traced back to abstract symmetries discovered by mathematicians and theoretical physicists. The interplay between Noether's theorem, Yang-Mills gauge theory, and the requirements of anomaly cancellation reveals that the electron's charge is deeply rooted in the fabric of reality. These connections are not merely theoretical constructs, they manifest in precise experimental measurements, from Penning trap experiments that measure the electron's charge-to-mass ratio with incredible precision, to observations of particle interactions in high-energy colliders. Each experimental confirmation serves as a subtle echo of the underlying symmetries that dictate particle properties. Reflecting on this interplay, we see a universe in which the electron's charge is stabilized not by chance, but by a profound coherence of mathematical laws. Symmetry is not a decorative feature of nature, but a guiding principle, ensuring that particles interact predictably, that charges remain conserved, and that the structure of matter is consistent throughout space and time. It is both humbling and exhilarating to realize that the negative charge on the electron, an invisible property of a subatomic particle, emerges naturally from these elegant principles, linking the smallest scales of quantum fields to the grand architecture of the universe itself. Through Noether's insight and the development of gauge theories, we understand that charges are not arbitrary labels but quantities constrained by symmetry, conservation, and consistency. This perspective bridges the gap between measurement and theory, showing how the discrete, uniform charge of the electron is a necessary consequence of the universe's underlying order. It prepares the ground for exploring even deeper theoretical frameworks, where grand unification, string theory, and topological field theories may one day reveal why the elementary charge assumes exactly the value that it does, providing a glimpse into the most fundamental architecture of reality. In the modern era, measuring the electron's charge has become a triumph of precision and ingenuity, pushing the boundaries of what can be observed and quantified. One of the most sophisticated tools for this purpose is the Penning trap, a device that uses a combination of strong magnetic and electric fields to confine a single electron in space. By carefully controlling the magnetic field and observing the electron's oscillatory motion, physicists can determine both its charge and mass with extraordinary accuracy. These experiments, conducted in laboratories around the world, reveal the remarkable consistency of the electron's charge, confirming that it is identical for every electron and stable under all observed conditions. Complementing the Penning trap are single electron transistors, devices capable of detecting and manipulating individual electrons one at a time. Developed through decades of experimental progress in nanotechnology, these transistors allow researchers to observe the transfer of single charges across a circuit, providing both a direct measurement of the electron's fundamental charge and a powerful tool for investigating quantum behavior in materials. These experiments not only refine our understanding of the electron, but also have practical applications, forming the foundation for emerging quantum computing technologies and nanoscale electronics. Another pillar in the modern measurement of electron charge is the quantum Hall effect, discovered by Klaus von Klitzing in the year 1980. In this phenomenon, a two-dimensional electron system subjected to extremely low temperatures and strong magnetic fields exhibits precise, quantized values of electrical resistance. The quantization is so exact that it serves as a reference standard for measuring the electron's charge and the fine structure constant. Institutions such as the National Institute of Standards and Technology in the United States and the Physikalische Technische Bundesanstalt in Germany have used these effects to achieve measurements of unparalleled precision, establishing the electron charge as one of the most accurately known constants in all of science. The interplay between experimental ingenuity and theoretical framework is critical in these measurements. By determining the electron's charge with such precision, researchers are able to test predictions from quantum electrodynamics, gauge theories, and the Standard Model itself. Slight discrepancies could indicate the presence of new physics, revealing subtleties beyond our current understanding. In this way, the rigor of measurement serves not merely as verification, but as a probing tool, challenging theoretical models and refining our conception of fundamental constants. Modern experiments are also remarkable for the sheer scale of control they require. Maintaining a single electron in a Penning trap demands stabilization of electromagnetic fields to parts per billion, isolation from vibrational noise, and precise temperature regulation. Single electron transistors operate in similar regimes, with careful fabrication of nanostructures and cryogenic environments to observe individual charges. These feats underscore not only the stability of the electron's charge, but also the sophistication of contemporary experimental physics, where a particle smaller than a billionth of a meter can be held, tracked, and studied with astonishing fidelity. The measured value of the electron's charge, approximately 1.602 times 10 to the negative 19th coulombs, is now so precise that it defines the scale of many other physical constants. It enters into the calculation of the fine structure constant, a dimensionless number characterizing the strength of electromagnetic interactions, which has been measured with remarkable agreement across different experimental methods. The electron's charge also informs our understanding of atomic spectra, the behavior of semiconductors, and the interactions of particles in high-energy colliders. Its consistency across all experiments reinforces the universality of physical law and provides a solid foundation for both practical technologies and theoretical investigations. High-precision measurements of the electron's charge continue to be a frontier of science. Laboratories worldwide, from Europe to the United States, perform experiments that refine the value and test its invariance under extreme conditions. These efforts demonstrate the remarkable stability and universality of the electron, reinforcing the idea that nature imposes strict order on fundamental properties. The methods may evolve, incorporating ever more sophisticated trapping techniques, nanoscale electronics, and quantum measurement protocols. But the underlying principle remains. The electron's charge is a constant, and its precise determination illuminates the harmony between theory and observation. In reflecting on these modern experiments, it is striking how far physics has come since Millikan's oil drop experiment in the year 1908. From suspended oil droplets to single electrons held in electromagnetic traps, from careful observation of deflected cathode rays to quantized conductance in two-dimensional electron systems, each advance represents a leap in both understanding and capability. And yet, despite all this progress, one question remains. Why does the electron have exactly this charge? Modern measurement tells us with incredible certainty what the charge is, but the deeper reason for its precise value continues to inspire theoretical exploration, from symmetry principles and gauge theories to the speculative frontiers of grand unification and string theory. The electron's charge is both a measured fact and a doorway into the profound mysteries that still lie at the heart of physics. Among the most intriguing numbers in all of physics is the fine structure constant, commonly denoted by the Greek letter alpha. This dimensionless constant, approximately 1 divided by 137, represents the fundamental strength of electromagnetic interactions and intimately connects to the charge of the electron. Unlike quantities measured in meters or kilograms, alpha has no units, making it a pure number that characterizes how electrons and photons interact. The electron's charge, together with Planck's constant and the speed of light, enters directly into the definition of this constant, linking a simple, measured property to one of the deepest relationships in nature. Physicists have long been fascinated by alpha precisely because it is dimensionless. Frank Wilczek, a Nobel laureate known for his work in quantum chromodynamics, has described alpha as a number that the universe seems to have picked out, a mysterious quantity that governs the intensity of electromagnetic phenomena across the cosmos. Its numerical value is neither zero nor infinity, but a moderate fraction, and it appears to be finely tuned to allow atoms, chemistry, and ultimately life to exist. This combination of simplicity, universality, and apparent arbitrariness makes the fine structure constant a focal point for both experimental measurement and theoretical speculation. One of the reasons alpha captures the imagination of physicists is that it offers a window into a realm beyond direct measurement. It is one thing to measure the electron's charge with a Penning trap or through the quantum Hall effect, but it is another to ask why alpha itself has the value it does. Could this constant, and therefore the electron's charge, emerge from deeper principles? Theoretical physicists have proposed that alpha might be tied to the geometry or topology of spacetime itself, ideas that emerge in theories such as string theory or higher dimensional frameworks. In these approaches, the familiar properties of particles are not fundamental inputs, but consequences of the shape and structure of additional spatial dimensions, curled up in ways too small to observe directly. String theory, for instance, suggests that the vibration modes of tiny strings determine the mass and charge of elementary particles. In certain models, the fine structure constant could correspond to ratios of geometric lengths or areas within these compactified dimensions, or to the flux of fields threading through topologically non-trivial shapes. Such perspectives hint that the electron's charge might not be an arbitrary number plucked from reality, but the result of deep mathematical relationships embedded in the fabric of the universe. Although experimental verification of these ideas remains beyond current technology, they provide a framework for connecting the constants we measure to fundamental principles of geometry and symmetry. In addition to geometric interpretations, alpha plays a crucial role in testing the limits of quantum electrodynamics, the theory that describes the interaction of electrons and photons. The precision with which the fine structure constant can now be measured through atomic spectroscopy, the anomalous magnetic moment of the electron, and the quantum Hall effect is astonishing, reaching parts per billion. These measurements serve as a benchmark for the consistency of our theories. Any deviation could hint at new physics, perhaps revealing hidden particles, subtle interactions, or connections to phenomena predicted by grand unified theories. The interplay between measured alpha, the electron's charge, and theoretical predictions exemplifies how experimental rigor informs high-level speculation. The fascination with alpha extends into cosmology as well. Some researchers have considered whether the fine structure constant might vary over cosmic time, subtly changing across billions of years as the universe evolves. Observations of distant quasars and the spectral lines of interstellar gases suggest that if such variation exists, it is extremely small, reinforcing the apparent universality and constancy of the electron's charge. This stability underscores the remarkable coherence of physical law, suggesting that the same fundamental numbers govern atomic interactions, whether observed here on Earth or in a galaxy millions of light years away. It is worth reflecting on why a single number can be so deeply compelling. Alpha connects the small and the large, the laboratory and the cosmos, the measured charge of an electron to the structure of atoms, the propagation of light, and even the formation of molecules essential to life. Its dimensionless nature makes it a pure feature of the universe, unaffected by human conventions or units of measurement. The electron's charge, entering directly into alpha, is therefore both a measured quantity and a reflection of a broader cosmic order. Speculative physics beyond the standard model frequently returns to alpha as a central piece of the puzzle. In attempts at grand unification, for instance, theorists examine whether the strengths of electromagnetic, weak, and strong forces converge at high energies, implying relationships among fundamental constants. In string theory landscapes, compactification schemes and the shapes of Calabi-Yau manifolds can influence the apparent strength of interactions, potentially explaining why alpha, and by extension the electron's charge, assumes its precise value. These high-level theories remain largely theoretical, yet they illustrate how the constants we measure in laboratories may emerge from profoundly deeper principles, connecting mathematics, geometry, and physical law in a tapestry of surprising coherence. Ultimately, the fine structure constant reminds us that understanding the electron's charge is not only about observing a tiny particle or performing delicate experiments. It is about asking why the universe has chosen a particular framework in which electrons carry a negative charge of precisely 1.602 times 10 to the negative 19th coulombs, a number that fits seamlessly into the laws of physics, chemistry, and cosmology. Alpha serves as a bridge between observation and theory, measurement and speculation, and in doing so, illuminates the tantalizing possibility that even the simplest properties of matter may have explanations rooted in the deep structure of reality. It is a number that whispers the presence of hidden order, inviting curiosity, imagination, and ongoing exploration into the fundamental nature of the universe. In the year 1931, the brilliant British physicist Paul Dirac proposed a theoretical idea that would ripple through the foundations of particle physics for decades to come. He suggested that if even a single magnetic monopole existed, an isolated particle carrying a north or south magnetic charge, it would provide a natural explanation for why electric charge is quantized. Up to that point, physicists had observed that electric charge always appears in integer multiples of a fundamental unit, the electron's charge, but the reason for this strict quantization remained elusive. Dirac showed mathematically that the existence of a magnetic monopole implies that all electric charges must be exact multiples of a basic quantity, elegantly linking two otherwise separate phenomena, the hypothetical magnetic monopole and the real, measured electron charge. The elegance of Dirac's argument is striking. He demonstrated that the mere possibility of a single monopole anywhere in the universe imposes a universal constraint on all electric charges, a concept that unites symmetry, topology, and quantization. In essence, the structure of the equations governing electromagnetism and quantum mechanics is such that if monopoles exist, then the discrete nature of electric charge is inevitable. This insight provides a rare example of a purely theoretical construct suggesting a universal feature of the physical world, an idea that is as beautiful mathematically as it is compelling conceptually. Later developments in the 1970s expanded upon Dirac's original vision. Physicists Gerard 't Hooft and Alexander Polyakov independently discovered that magnetic monopoles could arise naturally as solitons within certain gauge theories, particularly those connected to grand unified theories. These monopoles are stable, topologically protected solutions, arising from the structure of the field equations themselves rather than requiring an external assumption. In this context, the quantization of electric charge is not just a coincidence or a rule imposed by observation, it is a necessary consequence of the mathematical consistency of the theory. The work of 't Hooft and Polyakov showed that Dirac's ideas could be embedded in a broader framework, connecting the properties of individual particles to the symmetries of the universe at extremely high energies. Despite this theoretical elegance, magnetic monopoles have yet to be observed experimentally. High-energy particle colliders, searches in cosmic rays, and even deep underground laboratories designed to detect rare events have not produced definitive evidence of a monopole. Yet the absence of detection does not diminish the conceptual power of the idea. It demonstrates that the rules of nature can be dictated by possibilities as well as realities, that the very structure of quantum field theory can impose strict constraints on physical properties such as the electron's charge. Even in a universe where monopoles are exceedingly rare or hidden in inaccessible energy scales, their theoretical existence provides a profound mechanism for understanding why charge is quantized. Dirac's monopole also resonates with broader themes in theoretical physics. It illustrates the deep connections between symmetry, topology, and conservation laws, showing that seemingly separate quantities, magnetic charge and electric charge, can be linked by the fundamental structure of field equations. It also serves as a bridge to speculative physics, suggesting that the values we observe for basic constants, like the electron's charge, may emerge from hidden structures or constraints that we have yet to explore experimentally. The idea that the electron's negative charge is not arbitrary, but constrained by deep mathematical principles, highlights the interplay between observation, theory, and possibility in our understanding of the universe. The connection to grand unified theories is particularly compelling. These theories attempt to unify the electromagnetic weak and strong forces into a single framework at extremely high energies, predicting relationships among particle charges and interactions. Within many GUT models, the existence of monopoles is a natural consequence of symmetry breaking during the early universe, linking cosmology to particle physics. The quantization of electric charge, as explained through Dirac's monopole and extended by 't Hooft and Polyakov, is thus not merely a laboratory phenomenon, but a feature embedded in the grand architecture of fundamental forces. Dirac's proposal also illustrates the subtlety and power of theoretical physics. By imagining a particle that has never been seen, he uncovered a principle that explains a deeply observed property of nature. The quantization of charge, which Millikan measured, and which defines the electron's negative charge, can be understood through the lens of topology and symmetry, rather than through direct measurement alone. It is a reminder that the universe is constrained by mathematical consistency in ways that may not be immediately apparent, and that some of the deepest truths about matter can emerge from logical reasoning as much as from experiment. Even today, the search for monopoles continues, from high-energy experiments at the Large Hadron Collider in Geneva to cosmic ray detectors scattered across the globe. Each effort tests not only the existence of these exotic particles, but also the principles underlying the structure of charge. While the electron's negative charge has been measured with exquisite precision, Dirac's insight reminds us that its value may be deeply rooted in the possibilities dictated by symmetry, topology, and the mathematical fabric of quantum field theory. It is a remarkable example of how a single theoretical idea can illuminate a universal property, linking the electron in a laboratory here on Earth to the profound architecture of the cosmos itself. In the landscape of theoretical physics, grand unified theories, often abbreviated as GUTs, represent a bold attempt to see the universe through a single, coherent lens. These models aim to unify the electromagnetic, weak and strong nuclear forces under a single framework, suggesting that at extremely high energies, these seemingly distinct forces are manifestations of a single underlying interaction. Among the earliest and most influential of these models is the SU5 model, proposed in the year 1974 by Howard Georgi and Sheldon Glashow. SU5 uses a mathematical group structure to organize the known elementary particles, elegantly embedding quarks and leptons into unified multiplets and revealing deep relationships among their charges. Shortly thereafter, the SO10 model emerged, expanding the unifying structure and including all particles of a single generation in one irreducible representation. The SO10 framework is remarkable for its ability to naturally incorporate the right-handed neutrino, a particle not observed at the time but later suggested by neutrino oscillation experiments. This extension allows for the possibility of neutrino masses and provides additional constraints on particle charges, further linking the electron's negative charge to a broader mathematical structure. Later still, the E6 model, a more speculative and mathematically rich theory, offered even more intricate symmetries and potential particle content, hinting at exotic particles beyond the standard model, and reinforcing the idea that the patterns we observe in charges may reflect a deeper unified order. Helen Quinn, working alongside Howard Georgi and others, made significant contributions to understanding how symmetry breaking within these models could explain the patterns of observed charges. Symmetry breaking occurs when a high-energy, unified state transitions to the lower energy world we experience, allowing forces to differentiate and particles to acquire distinct masses and charges. In this process, the electron's negative charge, the fractional charges of quarks, and the balancing of positive and negative charges in matter all emerge in a mathematically consistent way. These insights revealed that the universe's choice of charge values may not be random, but a consequence of symmetry and its breaking during the early moments of the cosmos. Grand unified theories also make intriguing predictions about phenomena not yet observed, offering both guidance and challenge for experimental physics. One notable prediction is proton decay, a hypothetical process in which a proton spontaneously transforms into lighter particles over extremely long timescales, potentially billions or even trillions of years. Experiments at underground laboratories such as the Super Kamiokande detector in Japan have searched for such decays without definitive results, placing stringent lower bounds on the proton's lifetime. Despite the absence of observed decay, the theoretical possibility remains a compelling consequence of unification, linking particle charges, force strengths, and the stability of matter in a single framework. Another feature of GUTs is the natural appearance of fractional charges for quarks. In the standard model, quarks carry plus 2/3 or minus 1/3 of the electron's charge, but the origin of these fractions is not explained. Within SU5 and SO10 models, these fractional values arise directly from the mathematical structure of the theory, reflecting the way particles fit into unified multiplets and the requirements of anomaly cancellation. The electron's negative charge, in contrast, is embedded in this structure as a whole unit, balancing the quark charges to produce electrically neutral atoms. This mathematical elegance shows how GUTs constrain possible charge values, ensuring consistency while leaving the precise numerical magnitude as an input derived from empirical measurement. Despite their beauty, grand unified theories remain speculative, extending far beyond the energies accessible to current experiments. The unification scales involved, often around 10 to the 15th giga-electron volts, are far beyond what even the most powerful particle accelerators can probe directly. Yet the insights provided by these models guide theoretical exploration and shape expectations for future discoveries. They suggest that the electron's charge is not merely a convenient unit of measurement, but may reflect the deeper architecture of forces and particles, a consequence of symmetry principles and the early history of the universe. Mathematical consistency is at the heart of GUTs. The careful arrangement of particles into representations, the necessity for anomaly cancellation, and the unification of coupling strengths all point to a universe constrained by elegant rules. The electron, with its well-defined negative charge, occupies a precise place within this structure, balancing the other particles and interacting in ways dictated by symmetry. The fact that these theoretical predictions match observed properties so closely reinforces the idea that the patterns of charge are not arbitrary, but encoded within the universe's fundamental architecture. It is worth considering the speculative nature of these ideas alongside their conceptual power. While we may not yet be able to create the energies required to test these theories fully, the framework they provide is deeply satisfying. Grand unified theories offer a lens through which the electron's charge can be seen not as a standalone fact, but as part of a coherent and interconnected network of particles and forces. They suggest that every charge, every interaction, and every particle property may be a reflection of a deeper order, waiting to be revealed as our experimental and theoretical tools continue to evolve. In this way, GUTs bridge the gap between observation and speculation, between the measured electron charge and the possibility of discovering the underlying principle that dictates it. They show us that the universe's complexity can emerge from simple, elegant rules, and that even the most familiar particles are bound by structures of remarkable mathematical beauty. By embedding the electron within a grand unified framework, we glimpse how the universe might constrain fundamental constants, hinting at reasons for the electron's precise charge and inviting ongoing exploration into the hidden symmetries and connections that govern all matter. In the quiet depths of theoretical physics, string theory presents a vision of the universe in which the fundamental constituents of matter are not point-like particles, but tiny, vibrating strings. These strings, unimaginably small, on the order of the Planck length, around 10 to the negative 35 meters, can vibrate in different patterns, and each pattern corresponds to a different particle. A particular vibrational mode might manifest as an electron, another as a quark, and yet another as a photon or gluon. In this framework, the properties of particles, including their mass, spin, and crucially their electric charge, emerge naturally from the way these strings oscillate in the hidden fabric of spacetime. The electron's negative charge, for example, is a reflection of one of these specific vibrational states, a fundamental melody played across the dimensions of the cosmos. The development of string theory required careful attention to consistency and the avoidance of anomalies, mathematical inconsistencies that could render the theory invalid. In the year 1984, Michael Green and John Schwartz demonstrated that certain string theories could cancel these anomalies, ensuring that the framework could be consistent and predictive. Their work showed that the symmetries of string theory not only prevent mathematical contradictions, but also constrain the types of particles and their charges that can exist. This anomaly cancellation is a subtle mechanism, but it has profound implications. It ensures that charges like that of the electron are not arbitrary, but compatible with the deeper structure of a multidimensional universe. String theory introduces a landscape in which spacetime contains more dimensions than the familiar 3 of space and 1 of time. In many formulations, there are 10 or even 11 dimensions, most of which are compactified, curled up so tightly that they are imperceptible at human scales. The shape and topology of these extra dimensions influence the allowed vibrational modes of strings. Just as the shape of a violin determines the tones it can produce, the geometry of these hidden dimensions determines the spectrum of particle properties, including the electron's charge. A string vibrating along one pattern may produce a negative charge, while another configuration might correspond to a different particle entirely. In this sense, the electron's charge is tied not only to its own intrinsic properties, but also to the unseen architecture of the universe. These ideas offer a conceptual bridge to the standard model of particle physics. While the standard model classifies electrons, quarks, and other fundamental particles, string theory provides a deeper explanatory layer. In this framework, the properties that appear fixed in our four-dimensional experience, the electron's negative charge, the fractional charges of quarks, and the strengths of interactions, arise naturally from the geometry and topology of higher dimensions. Although the precise numerical value of the electron's charge is not yet predicted directly by string theory, the theory shows how charges can emerge as a consequence of fundamental principles rather than as arbitrary inputs. This connection offers the tantalizing possibility that someday the exact value of the electron's charge could be derived from first principles embedded in the structure of the universe itself. Visualizing these extra dimensions can be challenging, yet we can imagine them as intricate compact spaces, tiny and folded, influencing the behavior of strings just as a hidden labyrinth shapes the paths of those who walk through it. Each vibrational mode of a string resonates with the geometry of these spaces, producing the properties of particles we observe. The electron's negative charge is therefore like a note in a cosmic symphony, determined by the hidden harmonics of dimensions beyond our perception. The richness of these extra dimensions allows for a vast landscape of possible particles, interactions, and forces, suggesting that the universe's fundamental constants are deeply entwined with the shape and structure of reality itself. String theory is speculative, of course, and many of its predictions remain beyond the reach of current experiments. Yet it provides a framework for understanding why particles possess the charges they do, linking the electron's negative charge to profound geometric and topological principles. The elegance of this approach lies in its unifying potential. Rather than treating each particle property as a separate fact, it sees them as emergent from a single, coherent fabric. The mathematical sophistication of the theory, combined with its ability to accommodate all known particles and forces, underscores the possibility that the electron's charge is not an isolated number, but a consequence of deeper hidden structures. M-theory, an extension of string theory developed in the 1990s, further enriches this picture by proposing 11 dimensions and unifying different string theories into a single framework. In this context, branes, higher dimensional objects within spacetime, can influence the properties of strings and therefore the charges of particles. The electron's negative charge could be seen as the result of a string interacting with these branes in a specific configuration, an idea that, while highly abstract, provides a visualizable mechanism for how extra-dimensional structures dictate particle properties. This perspective invites us to imagine the universe as a multidimensional symphony with each particle playing a note determined by the hidden architecture of space-time. Ultimately, string theory and M-theory suggest that the electron's charge is not merely an isolated fact of measurement, but a manifestation of deep underlying principles. The vibrational patterns of strings, constrained by extra dimensions and anomaly cancellation, provide a coherent explanation for why electrons, quarks, and other particles carry the charges they do. While experimental verification remains a challenge, this framework offers a calm, conceptual narrative in which the electron's charge emerges naturally from the structure of the universe, connecting the observed properties of matter to the hidden, elegant geometry of higher dimensional space. It is a reminder that even the tiniest particle is intertwined with the vast, intricate design of reality, a subtle note in a universe composed of harmony, symmetry, and profound mathematical beauty. In the exploration of the deepest structures of physics, topology has emerged as a powerful tool for understanding why certain properties, such as electric charge, are quantized and stable. Topological quantum field theories, developed in part by Edward Witten and his collaborators, focus on global features of fields that remain unchanged under continuous deformations. These topological invariants are not concerned with local variations or small fluctuations. Instead, they capture the fundamental essence of field configurations. In this framework, charges, fluxes, and other conserved quantities can emerge as topological invariants, fixed by the structure of the fields themselves rather than by arbitrary assignment. The electron's negative charge, viewed through this lens, becomes part of a robust, mathematically constrained pattern that persists across all scales. Witten's pioneering work in the 1980s, often in collaboration with Greg Moore and Ashok Sen, demonstrated that topological features can impose strict conditions on the spectrum of allowed particles. For instance, the quantization of fluxes in gauge fields leads directly to the quantization of electric charges. This insight provides a high-level explanation for why electrons always carry the same negative charge, and why fractional charges, such as those of quarks, appear in precise ratios. Topology, in this sense, offers a conceptual bridge between abstract mathematics and the measurable properties of matter, showing that the patterns we observe are deeply rooted in the structure of fields that permeate the universe. Closely linked to topological considerations are dualities, profound relationships that connect seemingly distinct physical theories. S-duality, for example, relates strong coupling behavior in one theory to weak coupling behavior in another, providing unexpected insights into the symmetry and consistency of quantum field theories. Electric-magnetic duality is another powerful concept, suggesting a symmetry between electrically charged particles and hypothetical magnetic monopoles. These dualities imply that the allowed charges of particles are not arbitrary, but must satisfy deep consistency conditions imposed by the mathematical structure of the theory. In practical terms, the electron's negative charge is not just a random feature. It is constrained by these high-level symmetries and dualities, embedded in a network of interrelated rules that maintain coherence across the quantum world. Discrete symmetries, such as charge parity time reversal symmetry, further constrain the behavior of particles and the possible values of their charges. The careful balancing of these symmetries ensures that anomalies do not arise, which would otherwise disrupt the consistency of the theory. The work of Ashok Sen and other theorists has shown that discrete and continuous symmetries together can restrict the set of allowed particles, their interactions, and their charges. In this way, the electron's charge can be seen as a consequence not only of measurement, but of the underlying mathematical and topological architecture of the universe. Topological approaches also illuminate phenomena observed in condensed matter physics, such as the fractional quantum Hall effect. Here, quasi-particles carry fractional charges that emerge from the global topology of the electron fluid in two-dimensional materials under strong magnetic fields. The parallels between these emergent charges and fundamental charges in particle physics suggest that topology is a universal organizing principle, capable of constraining properties across vastly different scales and systems. In both cases, the stability and discreteness of charges arise from the topological structure of the underlying fields rather than from local arbitrary parameters. The conceptual beauty of these ideas lies in their ability to unify seemingly disparate phenomena. Topology, dualities, and exotic symmetries provide a framework in which the quantization of charge, the stability of fundamental particles, and the relationships among quarks, leptons, and gauge bosons all follow from underlying mathematical principles. The electron's negative charge, consistently measured across laboratories from NIST in the United States to PTB in Germany, can thus be understood as a natural outcome of these deep structures, rather than a mere coincidence or empirical input. These high-level frameworks also suggest pathways for further exploration. By examining topological invariants, dualities, and symmetry constraints, physicists can predict relationships among particles, explore the possible existence of new particles, and test the limits of quantum field theory. While much of this work remains theoretical, it provides a guiding principle for both interpretation and experimentation. The elegance of the mathematics ensures that any theory consistent with these constraints will necessarily reproduce observed charges, including the electron's negative charge, and may also hint at hidden structures yet to be discovered. In reflecting on this interplay of topology and symmetry, one appreciates the delicate balance between abstraction and observation. The electron's charge is not only measured in precise experiments, but is also encoded in the mathematical tapestry of quantum fields, shaped by invariant features that survive under deformation, constrained by dualities, and stabilized by symmetries. It is a subtle yet profound reminder that even the most familiar properties of matter are the result of deep, interconnected principles, bridging the world of high-level mathematics with the tangible reality of particles and forces. Through these ideas, we gain a richer understanding of why charge is quantized, why it is stable, and why the electron's negative charge holds its precise and universal value across the vast cosmos. In the realm of condensed matter physics, electric charge can manifest in ways that are both surprising and illuminating, offering analogies to the behavior of fundamental particles. One of the most striking examples is found in the quantum Hall effect, first observed by Klaus von Klitzing in the year 1980. When electrons are confined to two-dimensional planes and subjected to extremely low temperatures and strong magnetic fields, the system exhibits precisely quantized electrical conductance. In certain fractional regimes, quasi-particles emerge that carry a fraction of the electron's charge, revealing that charge, under specific collective conditions, can appear in smaller discrete amounts. These fractional charges are not isolated electrons but emergent excitations, collective behaviors arising from the interactions of many particles in a coherent quantum system. The theoretical understanding of these phenomena owes much to the work of Robert Laughlin and Horst Sturmer. Laughlin, in particular, proposed a wave function describing the ground state of a two-dimensional electron system under a strong magnetic field, demonstrating how fractional charge arises naturally from collective interactions. Sturmer's precise experimental work confirmed these predictions, showing the emergence of quasi-particles with charges such as 1/3 or 2/5 of the elementary charge. These findings not only provided insight into the behavior of electrons in constrained environments, but also offered a conceptual bridge to fundamental questions about charge itself, suggesting that under certain conditions, discrete units of charge emerge as a natural feature of interacting systems. Beyond the quantum Hall effect, topological insulators provide another compelling example of emergent charge phenomena. These materials act as insulators in their interior, but allow electrons to flow along their surfaces without dissipation, a property arising from the material's topological structure. Electrons on the surface are constrained by the global topology of the system, which protects their motion and ensures that they exhibit robust quantized behaviors. In these systems, the effective charge of surface excitations can be interpreted through topological invariants, linking the physical properties of electrons to abstract mathematical structures. This mirrors the ways in which topology in high-energy physics constrains fundamental particle charges, offering an intuitive laboratory analogy. The study of emergent charges in condensed matter systems provides valuable insight into the general principles of quantization. Just as the electron's negative charge is fixed and universal, fractional charges in quasi-particles arise consistently from the structure of the system. Both phenomena illustrate how discrete values emerge from deeper rules. For electrons, the rules are embedded in quantum electrodynamics, symmetries, and the architecture of the Standard Model. For quasi-particles, the rules emerge from collective interactions, topological constraints, and boundary conditions. By observing these analogies, we gain a more tangible understanding of how quantization works and why charges, whether fundamental or emergent, appear in fixed, reproducible amounts. Experimental methods in condensed matter physics allow us to probe these effects with extraordinary precision. Using ultra-clean semiconductor heterostructures, cryogenic environments near absolute zero, and strong magnetic fields, researchers can isolate and manipulate the quantum states responsible for fractional charges. The accuracy of these measurements, combined with the theoretical framework provided by Laughlin and others, enables scientists to observe these emergent properties in real time, linking abstract theory with concrete experimental evidence. Such work emphasizes that discrete charges are not just conceptual artifacts, but physical realities that manifest under appropriate conditions. The study of fractional and emergent charges also enriches our understanding of electron behavior in everyday matter. While the electron in an atom carries a fixed negative charge, its collective interactions in solids, liquids, or exotic quantum systems reveal new facets of how charge can organize, redistribute, and manifest in quantized units. Topological protection, fractionalization, and collective excitations illustrate that the concept of charge is not limited to a single particle, but is a property that can emerge from complex, many-body systems, echoing patterns found in the more fundamental realm of particle physics. By examining these condensed matter systems, we gain both intuition and inspiration. The emergence of fractional charges provides a visualizable and experimentally accessible analogy for understanding why the electron's charge is discrete and universal. It highlights the interplay between local interactions and global constraints, showing that even when systems are complex and composed of many constituents, fundamental patterns of quantization persist. In this sense, the behaviors observed in the quantum Hall effect and topological insulators mirror the stability and universality of the electron's negative charge, offering a bridge between emergent phenomena and fundamental constants. These insights also emphasize the power of topology, symmetry, and collective behavior in determining the properties of charges. In condensed matter systems, as in high-energy physics, constraints imposed by underlying structures lead naturally to discrete stable quantities. The analogy provides a calm and intuitive framework for thinking about the electron's charge. Whether in a laboratory, a semiconductor device, or the heart of a star, discrete charge emerges from the underlying rules of the system, whether those rules are written in the language of quantum field theory or in the interactions of many particles in a solid. In all cases, the principles of quantization, stability, and consistency govern the behavior of charge, uniting the emergent and the fundamental in a single conceptual thread. In the earliest moments of the universe, shortly after the Big Bang, the cosmos existed as a searing plasma of particles, a dense hot soup of quarks, electrons, protons, and photons. In this primordial state, the concept of electric charge played a crucial role in governing the behavior of matter and radiation. Electrons carried their negative charge, protons their positive charge, and the total sum of these charges in any sufficiently large volume remained balanced, creating an overall electrically neutral universe. This charge neutrality was essential for the formation of structures, ensuring that electromagnetic forces did not dominate the gravitational dynamics that would shape the cosmos on large scales. Cosmologists have long emphasized that even tiny deviations from perfect neutrality could have dramatically altered the evolution of the universe, preventing atoms from forming or disrupting the development of galaxies. Research groups studying early universe physics, including teams at the Institute for Advanced Study in Princeton and the Kavli Institute for Cosmological Physics in Chicago, have modeled the behavior of this plasma in exquisite detail. Simulations show that electrons, by virtue of their negative charge, play a key role in coupling radiation to matter, influencing processes such as photon diffusion and the damping of density fluctuations. These early interactions set the stage for the uniformity observed in the cosmic microwave background, as well as the subtle anisotropies that would eventually seed the formation of stars and galaxies. Without the precise and universal value of the electron's charge, the intricate balance required for these processes would be disrupted, leading to a cosmos that might look radically different from the one we observe. Charge quantization, so carefully measured in laboratories on Earth, also has profound implications for nucleosynthesis, the process by which the first atomic nuclei formed. During the first few minutes of the universe's existence, protons and neutrons combined to form helium, deuterium, and trace amounts of lithium, guided by nuclear forces and the distribution of electric charge. The electron's negative charge ensures the proper balance of electrons to protons, allowing atoms to emerge in stable configurations. If the charge was slightly different, chemical interactions and the balance of forces within nuclei would shift, altering the abundances of elements in a way that could prevent the formation of the diverse chemistry necessary for life. In this sense, the electron's charge connects directly to the large-scale chemical evolution of the universe, linking microphysics to the cosmos at grand scales. The stability of charge also has implications for the large-scale structure of the universe. Galaxies, clusters, and filaments are composed of vast numbers of electrically neutral atoms bound together by gravity rather than electromagnetic forces. The universality and invariance of the electron's charge ensure that matter behaves predictably over cosmic distances, allowing structures to form and persist. Electromagnetic forces, while immensely strong on atomic scales, cancel out in electrically neutral matter, leaving gravity as the dominant force shaping the cosmos. This delicate balance highlights how a microscopic property can influence the architecture of the universe, illustrating the intimate connection between the subatomic and the astronomical. Cosmologists also consider hypothetical scenarios in which charge might vary. Observations of distant quasars and intergalactic plasma suggest that the fine structure constant, intimately connected to the electron's charge, remains remarkably consistent across billions of light years. This constancy reinforces the idea that the electron's charge is not only precise in laboratories on Earth, but also universal throughout space and time. Such stability ensures that atoms formed in the early universe have the same properties as those found in stars today, maintaining the continuity of chemistry, physics, and the processes that sustain life. The study of the early universe also brings forward fascinating insights from plasma physics. Electrons in the primordial plasma interacted with photons through Thomson's scattering, exchanging momentum and energy in ways dictated by their charge. These interactions influenced the acoustic oscillations of the plasma, leaving imprints that are still visible in the cosmic microwave background. Measurements of these oscillations by missions such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite provide indirect confirmation of the electron's properties, linking cosmological observation with subatomic physics. The charge of a particle smaller than a billionth of a meter contributes directly to patterns observed across the entire observable universe. In addition to observational evidence, theoretical work emphasizes the necessity of quantized charge for cosmic evolution. Physicists exploring baryogenesis and the asymmetry between matter and antimatter recognize that the precise values of particle charges constrain possible reactions and decay processes in the early universe. The electron's charge, by setting the scale of electromagnetic interactions, ensures that these processes unfold in ways compatible with the existence of stable matter. Without such consistency, protons and electrons might not form stable atoms, and the universe would remain a diffuse, inhospitable plasma. Through this lens, the electron's negative charge can be seen as a thread woven into the very fabric of the cosmos. It shapes interactions at microscopic scales, governs the emergence of atoms and nuclei, influences the propagation of light through plasma, and contributes to the formation of galaxies and clusters. Charge quantization is not a local curiosity but a cosmic principle, ensuring that the universe evolves coherently from its earliest moments to the present day. By bridging microphysics and cosmology, we gain a sense of the profound unity of nature. The same property that defines an electron in a laboratory also governs the behavior of matter on the larger scales, linking the smallest constituents of reality to the vastness of space and time. Reflecting on this perspective, it becomes clear that the electron's charge is more than a measured constant. It is a fundamental feature that underpins the universe's structure and evolution. Its stability, universality, and quantization provide the foundation for chemistry, astrophysics, and cosmology alike. From the searing plasma of the early universe to the formation of stars and galaxies billions of years later, the electron's negative charge ensures that matter behaves predictably and consistently, demonstrating how a microscopic property can shape the cosmos in ways both subtle and profound. It is a reminder that the constants of nature, while measured in laboratories, echo across the universe, connecting the very small to the very large in a harmonious and elegant tapestry. Physics, at its most imaginative, often ventures into territories where speculation and rigorous theory intersect. One such frontier is the exploration of alternative models that attempt to explain why fundamental particles, like the electron, carry the charges they do. Among these ideas are preon models, notably the Harari-Schuper model developed in the year 1979. This theory proposes that quarks and leptons, usually considered fundamental, might themselves be composed of even smaller constituents called preons. In this framework, the electron's negative charge arises from the arrangement and interactions of these more elementary building blocks, suggesting that charge is emergent from a deeper layer of structure. The conceptual appeal of preon models lies in their ability to unify the patterns observed in particle charges. Quarks carry fractional charges, leptons carry whole units, and the intricate relationships between them might be explained by simple combinations of preons with discrete charge assignments. The Harari-Schuper model, for example, assigns preons charges of +1/3 or -1/3, and the combination of three preons produces the known charges of quarks and leptons. While elegant in its mathematical simplicity, this approach faces significant experimental challenges, as no preons have yet been observed, and the energy scales required to probe such structures are far beyond current particle accelerators. Nevertheless, the idea persists as a thought-provoking alternative, illustrating the human drive to seek patterns and deeper explanations. Beyond preon theories, some physicists have explored the possibility that fundamental charges might not be absolutely fixed, but could vary under extreme conditions or across cosmic time. These varying charge hypotheses are largely speculative, but arise naturally from attempts to reconcile cosmology with quantum field theory. For instance, in certain frameworks involving extra dimensions or evolving scalar fields, the effective value of the electron's charge might subtly change as the universe expands or as fields evolve in time. Such proposals remain hypothetical, and observational evidence from atomic spectra in distant galaxies constrains any variation to be extraordinarily small. Yet the mere consideration of these possibilities reflects the openness of physics to exploring the limits of known constants. Several lesser-known theorists have contributed to these speculative models, offering perspectives that complement mainstream approaches. For example, Jogesh Pati and Abdus Salam considered ideas of extended symmetries that might constrain particle charges beyond the standard model, while Yakov Zeldovich and others explored cosmological implications of varying fundamental constants. Each of these contributions demonstrates the interplay between theoretical creativity and empirical constraint, revealing the lengths to which physicists will go to find deeper principles underlying the observed properties of matter. These thinkers, though sometimes overshadowed by the giants of the field, enrich the conversation and exemplify the human curiosity that drives scientific inquiry. The broader value of these alternative theories lies not necessarily in immediate experimental confirmation, but in the way they frame questions. By imagining preons or varying charges, physicists explore what it would mean for nature to operate under different rules, and what principles might govern the electron's negative charge in a universe with deeper structure. This approach encourages careful consideration of symmetries, conservation laws, and the mathematical structures that could underlie reality. Even without direct evidence, these models act as intellectual laboratories, allowing scientists to test the consistency of ideas and to refine their understanding of what is fundamental. Speculative models also highlight the interplay between simplicity and complexity in physics. While the standard model successfully describes the charges of electrons, quarks, and other particles, it treats these charges as input parameters rather than derived quantities. Preon models, varying charge hypotheses, and other unconventional frameworks attempt to reduce this apparent arbitrariness, seeking a more unified explanation. The challenge is that simplicity at one level can imply complexity at another. Introducing preons requires additional particles, interactions, and symmetries, all of which must remain consistent with experimental observations. Navigating this balance is a hallmark of theoretical creativity, demonstrating the subtlety and sophistication required to propose alternative explanations. Importantly, these ideas serve as a reminder that our understanding of the electron's charge is both precise and incomplete. Experiments measure the value with extraordinary accuracy, yet the underlying reason for that precise number remains a mystery. Alternative theories do not replace the empirical facts. They complement them, providing conceptual frameworks that encourage exploration beyond established models. The electron's negative charge, in this light, becomes a bridge between observation and imagination, a concrete property that invites speculation about hidden structures and deeper laws. The calm, exploratory nature of these discussions also emphasizes the beauty of scientific curiosity. Physicists are motivated not simply by the desire to measure constants, but by the quest to understand why they exist as they do. The contemplation of preons, varying charges, and exotic symmetries reflects this drive, demonstrating that even in areas where direct evidence is scarce, intellectual rigor, mathematical reasoning, and creative thinking can illuminate new possibilities. These theories remind us that science is as much about asking profound questions as it is about providing definitive answers. By considering alternative and speculative approaches, we gain perspective on the electron's charge not only as a measured quantity, but as a feature with potential connections to deeper structures of reality. Whether through the arrangement of preons, the dynamics of evolving fields, or the constraints of extended symmetries, these models highlight the richness and complexity underlying even a single, seemingly simple property. They reveal the interplay between known laws and the space of possibilities, showing how curiosity, creativity, and careful reasoning together expand our understanding of the fundamental nature of matter and the subtle principles that shape the universe. As we reflect on the journey through the world of electric charge, it is remarkable to consider how a property so small and invisible shapes the universe in profound ways. From the first explorations of static electricity to the precise experiments of Robert Millikan in the year 1908, scientists have steadily uncovered the electron's negative charge as a fundamental constant of nature. J. Thomson's discovery of the electron, Eugen Goldstein's work with canal rays, and the meticulous measurements by Harvey Fletcher all laid the groundwork for understanding that charge is discrete, consistent, and universal. These historical milestones remind us that even the simplest questions, why does a particle carry this particular charge, can lead to insights of astonishing depth. Laboratory experiments have refined our knowledge of the electron's charge to a degree of precision that is breathtaking. Penning traps, single electron transistors, and quantum Hall effect measurements conducted at institutions such as NIST in the United States and the Physikalische Technische Bundesanstalt in Germany demonstrate not only the stability of charge, but also the ingenuity of experimental physics. These techniques allow researchers to observe individual electrons, manipulate them with extreme precision, and verify that their charge is identical everywhere in the observable universe. The electron's negative charge is therefore both a measured fact and a reflection of a deep order in nature, one that persists across scales from the tiniest laboratory apparatus to the vast reaches of interstellar space. Theoretical exploration adds further layers of fascination. Classical electromagnetism, governed by Maxwell's equations, provides the groundwork for understanding forces and fields, but fails to explain why charge is quantized. Quantum mechanics, through the insights of Wolfgang Pauli, Niels Bohr, and others, demonstrates that discrete particle properties naturally emerge at microscopic scales. The Standard Model, refined by Sheldon Glashow, Abdus Salam, and their collaborators, organizes electrons, quarks, and other fundamental particles, constraining their charges while leaving the precise magnitude of the electron's charge as an empirical input. These frameworks provide clarity and predictability, yet they also point to deeper mysteries, hinting at underlying principles that remain to be discovered. Explorations into high-level theoretical physics extend our understanding even further. The connections between symmetry, Noether's theorem, and gauge principles illustrate how charge conservation is rooted in the invariances of nature, while Dirac's proposal of magnetic monopoles and subsequent work by Gerard 't Hooft and Alexander Polyakov provide elegant if speculative explanations for charge quantization. Grand unified theories, including SU5, SO10, and E6 models, show how the relationships between quarks and leptons arise from unified symmetries, with contributions from Howard Georgi and Helen Quinn illuminating the links between symmetry breaking and charge assignments. String theory, M theory, and the exploration of extra dimensions, advanced by Michael Green and John Schwartz, suggest that the electron's charge may emerge from the vibrations of strings constrained by higher dimensional geometries, revealing a cosmos in which seemingly simple properties are connected to the hidden architecture of reality. Even more speculative ideas, such as preon models proposed by Harari and Schupe, and varying charge hypotheses explored by lesser-known theorists, reflect the curiosity and creativity of physicists striving to find deeper explanations. These approaches, while unconfirmed experimentally, demonstrate the human drive to understand not just the behavior of particles, but the principles that dictate their fundamental properties. They remind us that science is a balance between observation, rigorous reasoning, and imaginative exploration, and that unanswered questions are as valuable as confirmed facts in guiding intellectual inquiry. Condensed matter, physics provides additional insight, offering analogies that make the abstract concept of quantized charge more tangible. The fractional charges of quasiparticles in the quantum Hall effect, studied by Robert Laughlin and Horst Sturmer, and the emergent charge behavior in topological insulators illustrate that discrete, stable charges can arise from collective interactions and topological constraints. These systems echo the principles governing fundamental charges, reinforcing the idea that quantization is not accidental, but a natural consequence of underlying rules, whether in the microcosm of the laboratory or the vastness of the universe. Cosmology further emphasizes the universality and importance of the electron's charge. In the primordial plasma of the early universe, charge neutrality ensured the smooth evolution of matter, while the stability of electron charge influenced nucleosynthesis, the formation of the first atomic nuclei, and the emergence of large-scale structures such as galaxies and clusters. Observations of the cosmic microwave background and the distribution of elements across the cosmos confirm that the same charge observed in laboratories today played a vital role in shaping the universe from its earliest moments. Through this exploration, one sees that the electron's negative charge is both precise and mysterious. It is a measured constant that defines the behavior of atoms and molecules, powers the technologies of our modern world, and contributes to the evolution of stars and galaxies. At the same time, its exact value remains a question that inspires curiosity, driving investigations from quantum electrodynamics to speculative theories of unification, extra dimensions, and topological constraints. Contributions from both well-known and lesser-known scientists, as well as imaginative theoretical proposals, collectively illuminate the depth, complexity, and elegance of this fundamental property. Ultimately, reflecting on the electron's charge invites a sense of wonder at the coherence and beauty of the universe. From the first laboratory measurements over a century ago to the highest energy theoretical models of today, we observe a constant that is at once measurable, universal, and deeply tied to the underlying laws of nature. It encourages curiosity, critical thinking, and appreciation for the ongoing pursuit of knowledge. In this light, the electron's negative charge is more than a number. It is a window into the structure of reality, a subtle reminder that even the smallest features of the cosmos carry profound significance, and that the elegance of physics is a gift we continue to uncover, one discovery at a time.